All right, good morning. So I published the syllabus. Is right? Yeah. Anyone have a chance to look at this? Look through it already? Yes, so there is an optional textbook. Let me go back as well to the resources page. So I have here a bunch of resources. And so here I have some optional textbooks if you are interested. And then also some textbook for Verilog and then other learning resources. So throughout the quarter, totally welcome to go through these. I'll probably reference them. You may also have some like practice test questions that I pull from the textbooks. I don't recommend that you buy these. I would recommend just trying to like find something online because we won't use them enough to like warrant you spending money on them. Also, the Harris & Harris textbook, this is kind of the gold standard for like all digital design stuff, but they're releasing the next edition of it very soon, and the next edition is going to be much better. They've been working on it for many years, and so so look out for the newest edition of Harris & Harris. I don't recommend getting the second edition. Anyways, okay, it's a little lore for you. Good, so here's the syllabus. So I've not yet added you all to the Piazza and Gradescope, but I will do that immediately after class, and so then you will be able to upload your files, or maybe I did, I don't remember, but you should be able to gain access to that by the end of today. So I wanted to quickly go through the learning outcomes with you. So in this class, in this class, you should be able to describe the difference between a programming language and a structural hardware description language. So do you remember what the hardware description language that we will be using in this class is called? The hardware description language? Verilog? Yeah, Verilog. So in this class, instead of using a programming language, we're using a hardware description language, which describes hardware. And so good, okay. So we probably already have this first thing already checked off. And then past that, you'll learn how to use Verilog. So use the hardware description language to implement combinational and sequential circuits. We will learn about that later. You should also be able to do simple serial communication. You should be able to interpret and generate waveforms. So a waveform is, if anyone's used like an oscilloscope, you have like a graph of time versus voltage versus time, where you just see how the voltage changes over time. And that is kind of the main way that hardware engineers will debug and just look at the behavior of their circuits. So you'll spend time looking at waveforms. And then also, you should be able to interpret timing specification diagrams. We'll talk about this later. And you should also be able to describe circuit quality metrics and identify potential ways to improve/optimize the quality of digital circuits. So these are all the goals. So by the end of this class, you should be able to be able to create digital circuits and be able to do anything on this list. Okay, good. So all class communication will be done through Piazza. So please do not email me. If you email me, then I will probably not respond. Or you'll get like a very simple response that's like, ask me this on Piazza or something. The main reason for that is because I get so many emails. On Piazza, it will give me like a big, like in red, bold, like, help, I need this question answered. If it's on email, it'll like get sent to like the third page by the end of the day. So yeah, please post everything on Piazza. Also, that way, if a student maybe knows the answer, or if one of the TAs or someone else knows the answer, it's just going to be way more efficient for everyone. So please use Piazza. So I'll get you all on the Piazza soon. The labs start this week. They are 2 times per week. So it's both Tuesday and Thursday. However, labs are not, the attendance is not taken. What you will find is as the labs go on, you may be spending a lot of time in the lab, not actually during your lab time. You will have full access to the lab starting today, so you will be able to just go into the lab whenever you want, and in the lab you have the FPGA board and you will have all the computers with all the software already pre-installed on it. So you want to go into the lab and just use those computers. You are welcome. I did post an explanation of how to get all the software on your own computer, but it's kind of a hassle. Takes a lot of time to kind of figure out. So you can do that if you want. You can get all the software on your own computer, or you could probably just save that time and just go into the lab instead. I kind of just recommend that. Yes, so they start this week. You must complete complete the first lab is due this Thursday. So it's already we're in the swing of things. Okay. So assignments. So we have 20% of the grade goes to homeworks. I'll kind of let you read through this, but I'll skim through it kind of quick. The midterm will be October 30th, which is like right before Halloween. But you will have then that Friday off, so hopefully that is a good compromise. The final is on December 11th and is worth 20% of the grade. The labs are worth 45% of the grade, and so let's take a look at this. I'm trying to remember. Yes, okay. So sorry. Yes. Okay. Cool. I was on the fence about this, but I did decide. So in the past, in previous quarters, you must have needed to complete all lab demos in order to pass this course, which meant that this class has a notorious reputation and has an extremely high drop, withdrawal, fail rate, because if you miss even one single lab, then you're dropped from the course. So it's pretty intense. However, there's going to be a slight change in that the final week of this course, there's not going to be a lab due, and instead it will be a makeup period where you are able to turn in, if you happen to miss one single lab, you're welcome to turn in that lab for full points at the end of the quarter. However, if you miss 2 labs, then unfortunately you fail the course. So it's a little bit more lenient than it has been in the past. You will not be automatically dropped if you fail a lab, but you must pass every single lab at least by the end of the quarter. So I think right here I mentioned it. Yeah, so Friday of week 10, so December 6th. December 6th is the final deadline to get in your very last lab. So if you are worried though, so one nice thing about you being dropped automatically is that on your record, it just shows that you dropped a class or you withdrew from the class. Most likely, if you get to the end of the class and you're missing like multiple labs, you're probably going to fail, right? So it's on you now. It's your responsibility to make the decision to either withdraw or drop early so that you don't have an F on your transcript. Instead, you just have a withdrawal. So it's putting a little bit more responsibility on you. It's a little bit more lenient now that you can turn in one lab late. But yes, it's still quite intense. So good luck with this. We'll see kind of how it goes. We're trying to kind of change up the rules of previous from what it was in previous quarters. I'm not sure how much of this class you've heard before. So anyways, okay, that's enough about that. Okay, and then last thing. So there's now a 5% participation grade. So in lecture, occasionally, I will throw out like a pop quiz, and you all have to complete it on the spot, and it will all be graded for completion. So not actually for correctness. It's just to make sure that you're engaged. But I highly recommend that you put in as much effort as you can into those pop quizzes so that later on when you're studying for the midterm and for the final, you have that resource and so good, okay. Most likely we'll have them today. Haven't decided yet. Okay, and here is the schedule of everything. I'll let you read that on your own. This factors in all of the different holidays that we have this quarter. And okay, so then everything else is kind of just standard stuff. So recommend you read through it. Probably want to read through the AI policy as well. Okay, good. Any questions on this?
Okay, so the lab section for when we go to so that is where we work on the labs and we get help and also go into
Exactly. Yeah. Great question. Yeah. So the only time that TAs and tutors will be in the lab are during Tuesdays and Thursdays during the established lab times. Yeah. So so in that time, you will want to go into the lab specifically for your checkoffs. So most likely, you will not be able to complete the entire lab just in your lab sections. You will need to also come into the lab later on, or like on Monday, Wednesday, Friday. And work on it then. And then finally, on Tuesdays and Thursdays, that's when you go and receive help, and that's when you do your checkoffs. Yeah.
Will we get to take home the FPGA?
You cannot take home the FPGA in the lab, but you can rent the FPGAs through Bell's lab. I believe I put that in one of the tabs. If not, then I should. Let me just quickly check. Resources. Oh, I guess not. Okay. Yeah. I'll put it in the information. So yeah, the Bell's lab, I think it's like Baskin Engineering Lab or something. Anyways, they're responsible for all the different labs in Baskin Engineering, and they have a bunch of FPGAs, and you can rent them for $30 for the quarter. Then you can take them home. Then you will need to install all of the tools on your own computer, which kind of takes a while. So first, before you rent any of the FPGAs, I highly recommend just trying to make sure that you actually have all the tools installed, because a few people last quarter, they would rent the FPGA and then realize that they couldn't figure out how to install all the tools, and now they just had this FPGA that they couldn't use. So yeah, step one is try to install the tools first, and then rent the FPGA if you want to do that route. Honestly, I just recommend just doing it all in the lab. Yeah, question.
So how does the 24 get access to the lab?
You will receive an email about that. You'll receive a code, and you will just punch in the code into, there's like a little keypad that you put into the door knob, and then you'll get in.
Does that start today?
It will start today, yeah. Yes.
You know the lab is open 24/7, or is there?
You have 24/7 access with your code. Yeah. Okay, yeah.
For the makeup week, like
Uh-huh.
the labs, is that the same thing as that late pass? Or is those like two separate things? Like, are you
Exactly.
late pass on
Yeah.
the week?
Exactly. Yeah, so the late pass, I'm saying in the final week, that's probably when you want to actually work on the lab. Yeah. Cool. Yeah.
Will lectures be recorded?
Lectures will be recorded, and the first lecture has already been posted to Canvas. Although I forgot to. Oh, you know what? This is unfortunate. I was going to say that I forgot to record the screen, so it's just audio. I just realized I'm doing the same thing today as well. So let me turn on the video so you can see my screen as well. But yes, they are. I post them on YouTube just because I like YouTube's playback system the most. But yeah, they're right here, lecture recordings. So it'll pull up a YouTube playlist. Okay, good. Great. So I also posted the notes that I wrote out last lecture. So I have them right here, and I'm opening them, and they are right here. Yeah, so what do we talk about on Friday, I mean? Yeah.
So you're kind of talking about why study chip design.
Yeah.
You know, Moore's law and CHIPS Act and like.
Absolutely, yeah. So there's all sorts of reasons why we should be studying chips. Yeah, hopefully drilled into you that this is an awesome class and that you'll stay in this class. And then we also talked a little bit about adders. We talked about half adders and full adders, and then talked about how to create a sum of products from a truth table. So here is the truth table where we have our inputs. So we have X, Y, and Z, and it's just going through all the different possible values, all the permutations of whatever, all these, of the different ones and zeros that they could be. And then for each one of these inputs, we also wrote what the output was. So here, so carry, you can see, is only one when we have at least two ones set, or when we have exactly two ones set. No, at least two ones. Yeah, there we go. So Yeah, so then here's what we ended up writing. And then also notice that we can just create a sum of products by highlighting every single time that we have a 1 in the output of our truth table, and we can just write out that whole term. So this right here, this one represented this set of inputs right here, right? Or this term represented this set of inputs right here. Right? Yeah, cool, okay. You're gonna need this on your first lab, so remember that. Cool, so now we have these great circuits, and I'm gonna switch over to my iPad, and let's now like just kind of draw out what these circuits look like. So let's do the half adder first. So do we remember how to do the half adder? So if we have inputs A and B, what are the outputs? Yeah, C and sum. Okay. How do we get sum? Remember? Yeah.
XOR
Yeah, XOR. There we go. Okay. So XOR, and then for C, what do we have? How do we implement C? Yeah.
And an AB.
Yeah, and. I'll do a different color. Very cool. Very cool. So this is the circuit, right? And we've seen these. Have you seen these gates before? In 12, did you ever have to draw out like a schematic like this? Yeah. Okay. Sure. Well, let's think about this as more like digital designers. Let's say that the AND gate maybe takes, so just in general, when you have an AND gate, maybe in this universe, in this whatever, maybe this is TSMC's 65 nanometer AND gate. And so let's say that this runs at, like it has a delay of 3 nanoseconds. And in this XOR gate, maybe let's say that this runs in 10 nanoseconds. Okay. So how long would it take, let's say at time equals 0, boom, time equals 0, A and B become valid inputs. How long does it take for our output to be valid? Yeah, 10, right? Because they're both happening in parallel. So carry will actually be done when? Yeah, after 3 nanoseconds, but sum won't be ready for another like 7 after that. So it'll take a total of 10 nanoseconds in order for this to all become valid. Yeah, okay. And you know what, let's draw out a little waveform of that. Yeah, there we go. So if we have, let's say, something like that. So let's say this is 3, 6, 9, 12 nanoseconds. So these are all nanoseconds. And let's make this right here, this is going to be C. And this is 0 volts, and this is 1 volt. And then this will be S, this will be 0 volts, and this will be 1 volt. And let's add A and B as well. Okay. And also, yeah, let's shift this over just a little bit, just to give us some time to see A and B become steady. So let's say, so this is 0, right? So at this time right here, let's say we don't know what A and B are, okay? If we don't know what A and B are, then do we know what C and S are? No, okay, so at the beginning, we at least know that C and S are also going to be unknown. So this red like squiggle, I'm gonna say is just like, we don't know what this value is. But then, boom, let's say at time equals 0, A equals 1, so this is all 1 volt, and then B will equal 0 volts. Okay. So take a second. So how do we think we should fill out C and S? So go and actually speak with the person sitting next to you and see if you can figure out exactly what C and S should look like for the rest of this graph. So take about 30 seconds and just quickly chat and be like, oh yeah, I think it should look like this. Okay, go. So what's going to happen with C? Yeah.
Is it going to be like a squiggle line until 3 nanoseconds and then be 0?
Is that what we think? Is that kind of yeah, that's exactly what I was thinking too. So I think C, it's like, right, because it has a 3 nanosecond delay. So it's unknown for this whole time. But then boom, after 3 nanoseconds, now suddenly the data has fully propagated. And yeah, so we take this and this and this. So A and B, which is 0. So yeah, so 0 volts. So there we go. So this is all 0. And I'll just write it as 0, 0, 1. So it's clear. And then, okay, and then with S, it's going to be quite similar, right? So how long do we squiggle for? Yeah, for 10. Okay, so there we go. Looks like about 10 right there. And then what is the value after that? 1. Okay, cool. Yeah, cool. Very good. Right. Maybe let's zoom out a little bit. So maybe instead of like these very kind of short values, maybe let's make this 0, 10, 20, 30, 40. All right, so if A, let's say, once again, so it starts out at 1 and 0. Okay, but then after that, maybe it changes to 1, 1. Okay, cool. So let's do this together. So yeah, how long? Okay. So C. What's going to happen with C here? So remember, its delay was how many nanoseconds?
3.
Yeah, it was 3 nanoseconds. Okay. So that means it's going to probably be unknown for additional 3 nanoseconds. And then after that, it will switch to what value?
0.
Yeah, okay, because it's 0 and 1. So okay, so it's going to be 0. Good. We'll continue until, and then it changes right here again, right? So I'll make a little mark that's like, whatever, 20 nanoseconds. Okay. And then how long does it continue after that?
3.
Yeah, then it continues for another 3. So then finally at 23, what happens? Yeah, now it's going to be 1 and 1. So now I think it's going to switch up to 1 and continue. All right, cool. And then for S, what is going to happen here? Yeah, so it's going to squiggle for how many nanoseconds? 10. Yeah. Okay, so 10. And then after that, what happens? Yeah, it's going to be 1 because it's 0 XOR 1. Okay, now we're here. Then what happens? Yeah, great. It stays there for 10 more nanoseconds. Then finally, right here at 30, what happens? Yeah, cool. Very good. Okay, right? Makes sense? Pretty good. Let's zoom out further. you. Right, so now if this is like 100, 200, 300, 400, at this point, there's probably not going to be too much of a visible delay between A changing and C and S changing, because it's just going to take like a small little time on the span of 100 nanoseconds. Yeah, so if like A is like 0, and then switches to 1, and then back to 0 maybe, and then B, maybe something like this. Okay, what is C going to look like? Well, yeah, so if we just look at kind of these waveforms, so when should C be high? When should it be 1? Yeah, when they're both high. So it's only going to be just this tiny little section right here. So we can probably just kind of, and we can kind of ignore the delay in our diagram just because it's so kind of like small. Yeah, so then just right here, there's a little stretch that it goes high for, and it goes back down. Yeah, and notice, yeah, this is there's a 3 nanosecond delay. It's going from here to here. And a 3 nanosecond delay here to here. Yeah, and then similarly with this. So this is just when they are not equal to each other. So we'll go up, go down. Stays, no, sorry. There we go. Right? Great. These are the inputs. Good. Right? Or not right? There could be a mistake. Yeah. Oh, and then this delay, so how long is this delay right here from like A to this? Yeah, so this is 10 nanoseconds after A changed. And then this, whatever, this right here is also, yeah, 10. Yeah, and we could keep zooming out, right? But yeah, it's kind of interesting because like when you're on like really small scales, like it feels like the delay really matters. Yeah, and depending on what frequency maybe your clock is running at, or like yeah, depending on the precision of like how fine do you actually need your timing. Every single nanosecond matters. Like nanoseconds are super fast. What is the conversion from nanoseconds to seconds? No? Yeah. Yeah, 10 to the 9, right? So it's whatever, 1 billion nanoseconds in 1 second. So they're very small. But yeah, my entire life is basically just counting like how many nanoseconds my circuit will take. So that's, yeah, it's going to be your life now too. Okay, cool. So that is intro to little, yeah, waveforms. And so, yeah. Is the like analog circuits class required for this course? I don't remember. No. Has anyone done anything with like transistors before? No? Just a little bit? Yeah? Okay. Yeah, so maybe it'd be beneficial to just talk lightly about transistors, right? Because we have gates, but they were just kind of handed to you. It's like, oh, like assume we have an AND gate, assume we have a NOT gate, assume we have an XOR gate, right? Was that kind of just your experience in 12? All right.
We worked
Yeah.
a little bit with transistors as well.
Okay.
Like we did build like a NOT and an AND gate out of transistors.
Oh, good. Okay. Cool. Yeah, so maybe I was just going to walk through that very quickly. So, so a transistor is a 3-port device, and this is the symbol for specifically an NMOS transistor. So this is NMOS. And yeah, so this is the circuit diagram. But the way you can actually kind of imagine this is you have a so you have your silicon, right? And then you have some sort of insulator on top of that. And then on top of that, you have your metal. And then your silicon dioxide. Right. Yeah, and so whenever you think of a transistor, what you actually have is something that kind of is in this structure, where you have doped silicon at the bottom, and effectively what you will have is a structure where you have two diodes that, depending on how you dope your silicon, are either both facing out like this, or they're facing in like this. And this doesn't seem like a very good circuit, right? It's like two diodes pointing into each other. Not much is going to be happening, right? This is effectively just an open circuit right here. No current will flow. But as you add a voltage to your metal up here, what's going to happen is your diodes are just going to kind of disappear. And suddenly, as you bias your gate, so we call this the gate. So as you increase the voltage or decrease the voltage, depending on what transistor you have, you will just kind of disintegrate this diode, and it will kind of just look like a short circuit. So that is how transistors work at a high level.
Sorry, so that's like after a voltage difference is applied?
Yeah, exactly. Right. So after gate is biased. Yeah. Cool, okay. And I'm kind of speed running through this because it's not super important, but okay, I'm going to move on from this page. Yeah, so as I said, though, so there's two types of transistors. So you have NMOS transistors. You also have PMOS transistors. So this is a PMOS. This is an NMOS. And the way to use these, so remember, so I said that when you bias the gate, they become a short circuit, right? Like effectively, it's like flipping a switch. And so when you bias the voltage, or bias the gate, then it will close the circuit, and it will now become a short. So the way that you most effectively use these transistors is you should always attach one side of your PMOS to your power supply, which will most likely be 1 volt. And then for your NMOS, you should always hook this up to ground, so 0 volts. Okay, and then, so if we write out a truth table for what this is right here, so we'll call this, this is the drain, right here, drain, and this is the gate. So we can make a truth table for the gate versus the drain. So if the gate is 0 volts for a PMOS, then the drain is going to be 1. But if then that's inverted for the other way. Is that right? Oh, almost. Okay. So, okay. So you may imagine that you would just have 0 volts when your gate is set. But notice, so if we look back at this circuit, right? So we have the diodes here. Let's say that we have hooked up this side right here to 1 volt. Okay, so 1 volt is flowing in through here. But let's say that these diodes are active. So what is the voltage going to be over on this side? So in this circuit, right? So 1 volt comes through this diode. Maybe now it's dropped to like 1.8 volts. But then it can't go over this. So then what is the voltage going to be over here?
0.
Yeah, well, not quite, right? Because technically there's going to be a small capacitance to like just the earth, to just everything. So actually it's going to be charged to some unknown value. So it's either going to be 0 volts or 1 volt, could be 1,000,000 volts, could be anything. Yeah, so actually we don't know what this voltage is. So what we call this is high impedance. Because we just don't know, like, what this is. And it's not being discharged by anything. If it was a low impedance and it was being like, if there was like a low resistance that it was hooked up to, then it would fall to 0 volts. But instead, we say that this is high impedance. So that means that the gate is floating, and so what we'll need to do is have something else set it. So right now, with the PMOS, it looks like the only actual function that it has is just setting the output to 1. But the NMOS is cool because, if the gate is 0, then the drain will also be 0. Is that right? No, so sorry. I'm confused. Okay, sorry. If the gate is 1, yes, okay. If the gate is 1, then the drain becomes 0. But if the gate is 0, then the drain becomes high impedance. So from this, now, we can create a complementary circuit that uses both a PMOS and an NMOS, where the PMOS will only set whenever the circuit must be 1, and then the NMOS must set whenever the circuit must be 0. So let's do this for an inverter, right? So an inverter, the idea is whenever the input is 0, the output should be 1, or whenever the input is 1, the output should be 0, right? So go and see if you can combine these 2 functions right here to make sure that the PMOS is activated whenever the gate is 0, but the NMOS is activated whenever the gate is 1. So go and draw out a circuit on your notes. How can we create an inverter? So it kind of just falls into place, right? Like if we just take this PMOS and this NMOS, and I'll just draw it. So if we have a PMOS, so remember, so what should the PMOS always be hooked up to?
The source.
Yeah, well, so the source of the PMOS, what should the source of the PMOS be hooked up to? Just high voltage, yeah. So your power supply, yeah. So 1 volt, and then so great. So now it looks like already the PMOS is doing exactly what the inverter should do. Where if we plug in 0, the output will be 1. So that's good. So but now we just need to now set for when the gate is 1. So when the gate is 1, notice that the NMOS is going to drive it to 0. So just kind of this magical thing that creating an inverter is super easy because you can just kind of just hook these together. And so this right here is an inverter circuit where when this is 0, so if this is 0, is the NMOS or the PMOS activated? Yeah, if it's 0, right, then the PMOS is going to be driving the drain. So this is the drain. Yeah, it's going to be driving the drain as 1. But if this is 1, then is the NMOS or the PMOS activated now? Yeah, it's going to be the NMOS now. Yeah, very cool. So what's so great about this is, this structure right here, so this is called a CMOS inverter. And so CMOS, this is the driving force behind all of modern day transistor technology. The reason for that is because of how power efficient it is. Whenever it has received an input, it actually takes no static power at all to drive the output. So that the output, we can effectively just think of, like when we have 1 right here, we can effectively just think of this as like a direct short to ground. And so there's no extra power dissipation that occurs within the transistor. And yeah, similarly with the PMOS, if I now set the input to 0, then now the output is a direct short to the power supply. Yeah, question.
The power is only used for switching.
Exactly. Right. So, but it takes some charge still to just charge up that wire, like to charge up all your wires, and to change the capacitances within your transistors. So you only have switching power in CMOS, which makes it extremely power efficient. And yeah, this is why it has driven modern day technology. It's the reason why you can have billions of transistors on a chip. It's because actually most of those transistors are not actually doing anything. They're just like stuck in one single position. And maybe you only have a few thousand transistors actually switching every single clock cycle on your CPU. Yeah, CMOS, so very power efficient. Okay. Let's make an AND gate. Have you made an AND gate with transistors before? I assume that you've made an inverter before. Have you made an AND gate before? You have made an AND gate. All right, incredible. Let's do it. Should be easy. And actually, instead of an AND gate, we're going to make a NAND gate. So a NAND gate, so let me write this out. So if we have A, NAND B, it's the same thing as first ANDing them and then inverting them. So if you have 0, 0, 0, 1, 1, 0, 1, 1. So 0 and 0, what is the output going to be if you use an AND gate? It's going to be 0. So for a NAND gate, it will be what?
1.
Yeah, 1. Okay. And that goes for the rest of these as well, right? But then if you have 1 and 1, then what will the output of that AND gate be?
0.
So 1 and 1 is 1, but if you invert that, then you get 0. So good. So this is the truth table for a NAND gate. Okay. And I'll bring down the truth table for the NMOS and PMOS. Okay, I want you all to take a minute and try to remember how to do this / figure it out how to do it for the first time. So yeah, please create a NAND gate using multiple NMOS and PMOS. So remember, the PMOS can drive your 1s. So here are all your 1s, but your NMOS can only drive your 0. So here's the 0 output. So okay, begin. Start thinking about this. See if you can remember. let's see if we can just do the PMOS part first. Okay, so we should have a 1 be driven. Seems like any time that we ever have a 0, right? So if we ever have a 0, then we should have a 1 being outputted by the PMOS circuit. So how can we do that? So yeah, if we have like a PMOS that is being fed with A, and then maybe another PMOS that's being fed with B. Like how should we like arrange these? Yeah.
If we do them in parallel, then anytime either of them is split to 0, the output will be 1.
Yeah, right? So let's see that. So remember, we must always hook these up to a high voltage. Okay. Yeah, so it looks like if A is set to 0, right? So connect these in parallel. So if A is set to 0, then this is going to be set to 1 volt. And if B is set to 0, then this is going to be 1 volt. Yeah, so actually it looks like this exactly does it, right? This exactly will create a 1 for every single case that, that we have exactly 1 or more zeros. But what happens if they are both 1? Yeah, it's going to output a high impedance value. Right. Yeah, so then we need the PMOS circuit to drive 0 for the case when we have 1 and 1. So how can we drive 0, yeah, if we have 1 and 1? Yes?
What if we put 2 NMOS in series to go to ground?
Yeah, I really like that. So if we put NMOS and NMOS, hook up to ground, so this is A and B, right? So let's double check though, right? Because maybe something weird happened. So let's say that we have 0, 0. Okay, so 0, 0 should output 1. We've already established that this works. So this is currently outputting 1. But we definitely do not want this to output like 0. Because if this is outputting 0 and this is outputting 1, then we'll have like a direct tie from ground to your power supply. So, and that would be bad. So, okay, so let's make sure that they're completely disjoint from one another. So if we have, so 0 and 0, then what will happen? Remember? It's going to be an open circuit, right? Because up here, so if we look at the NMOS behavior, so yeah, if we're plugging in 0 and 0, then we're not going to have any sort of connection to ground. So actually, this is going to be open, and it's going to be high impedance, so we're good. Yeah. Let's check maybe, let's check 1, 1 now. So we have 1 and 1. I'll write it out. So if we have 1 and 1, so I think we established already that if we have 1 and 1 here, that the PMOS will not drive anything. They will be high impedance. But the NMOS, so remember, so when we have the NMOS set to 1, then now it drives to 0. So this B right here will correctly drive this to 0. But then we have this A as well, and now it's being hooked up to 0. All right, so there's like a little bit of delay. Like it took the time for this 0 to propagate through B. And then boom, okay, now it's propagated through B. And so now A effectively is like, tied to ground. And so now A is receiving 1. So if we look at 1, looks like we're good. So this is going now to tie it to 0. Yeah, okay, makes sense. Yes, cool. So I spent kind of good amount of time on that, I think. So hopefully we've all kind of caught up. I know, yeah, people are in like kind of different places on your CMOS experiences. But here we go. So looks like this NAND gate exactly works now. There you go. So this is our first transistor schematic in this class. You should all be very proud of yourselves. Excellent. Okay. What if we wanted to convert this to an AND gate? What would we do? Yeah.
I mean, can we like connect the CMOS inverter to it?
Yeah, that's what I'm thinking, right? So how would we connect the CMOS inverter to this? How would you see?
Yeah, like, just to convert the result into a
Say it again.
Are they like maybe at the very end?
Oh, uh-huh. So you're saying, so right here, so after the, so after this NAND gate has produced its value, right? So what do we do with this? Yeah, anyone else? How do we convert this to an NAND gate? Yes?
You put a knot after the NAND.
Sure. So can you be a little bit more specific? So here was our inverter circuit. So how do we just like put a knot? Like what?
Put that whole inverter circuit after the NAND.
Sure. Yeah. Okay. And what? I mean, and how do we?
The drain connects to the output of NAND.
Yeah. Close. Yes.
You could hook up the output of the AND to both the inputs of the inverter.
Exactly. Right. So you would hook it up to the gates, to the input gates. So you wouldn't hook it up to the drain. So you'd actually want to like kind of reverse this. So I'll just draw it one more time. Yeah. So you would have. Now, so it's the input of your PMOS and your NMOS right here. So now this is your final output. So this would be an AND gate right here. Yeah,
Is drain kind of like an output?
exactly. Yeah, drain is always your output. Yeah. Okay, cool. Makes sense. We're all good on this? Yeah. Cool. So that's why we were saying that the where was it? Yeah. So way at the top, way at the very beginning, I mentioned let's imagine that we have an AND gate that takes 3 whole nanoseconds to switch. Well, that's actually because all the transistors. So yeah, if we go back to this AND gate implementation that we did here, so this is our AND gate. There's a whole bunch of transistors in this that all need to flip. And each of them, like if they take like just a few picoseconds, I mean, it all kind of just adds up. Like if this is 100 picoseconds and these two are 100 picoseconds, like it all adds up. And then in the end, remember, so these wires have capacitances attached to them. Just like being a wire in the world is just every wire is actually a transmission line that is taking in voltages from everywhere else, especially if you have a chip that is like oscillating at like 100 like megahertz or maybe even a gigahertz. It's receiving all sorts of weird crosstalk and cross coupling, and so unfortunately, there's just a lot of like delays that are added into your kind of basic transistor circuits. And so that's why it kind of actually takes a while for all your transistors to switch. So so 3 nanoseconds for an AND gate is fairly typical, but they can go much faster than that. I would say most likely maybe closer to like 100 picoseconds or something. But depending on what year you're living in or what, how much money you're willing to spend to TSMC or Global Foundries or whoever. And then so if you were now to make like an XOR gate, you'd imagine that an XOR gate would be much, much more complicated than this. And so that's why the XOR gate took 10 nanoseconds in our basic example instead of just 3 nanoseconds. So okay, any more questions on this? Okay, we're gonna do a quick participation question. So please open up Canvas. Hopefully you have it accessible on your phones. And the question is, just like in the short answer part, hopefully, do you all see the assignment? Yeah, okay, cool. The question is, what is the benefit of CMOS? All right, and feel free to discuss it with the person sitting next to you if you don't remember exactly why we use CMOS. Yes?
I was wondering if there was like a different kind of RGB that might be more common.
There are, but you should only ever use CMOS. Yeah, the only time you would want a different structure is not for like large chips, but for like very small circuits. So if you're building, like one of them total on your entire chip, then it's fine. Or if it's like a power delivery thing, then it's fine. But if you have more than like 100 of them, then you always want to use CMOS. Yeah.